right, so this is the lecture 23. I did upload this if you want to go to the module 23 to look at these. So exam 4 is coming up. So not this Thursday because Thanksgiving. So next Thursday will be your last exam. So after that, December 10th, which follows the university guideline for final exams, you'll have an opportunity to take up to all 3 exams if you would like. So during that time, which will be December 10th, write that. So December 10th is your final option. So they are retake options for each exam. I should say each exam. So you will have 2 hours, 3:30 to 5:30. So during that time frame, you can take 1 exam, you can take up to all 4 of the exams if you want, but you will only have the 2 hours. So if you decide to take all 4, you're gonna have to do them very quickly. So any questions about that? So if you opt to take the exam, I always get questions like, does it replace for sure your other exam? I take the higher of the 2. So if you still did better in the midterm exam and you opt to take the final but don't do as well on that one, then I still use your midterm exam. So whichever one out of the 2 is the higher value. So that's the one I use for the end grading. For this exam 4, it will be the same structure as you've had before. So we'll meet in the Ingman lab. It will be on these RLC circuits, so you'll have both parallel or series configurations, and then with them they could be overdamped, underdamped, or critically damped, so any of those, and you will need to solve the circuits. So all that will be just the solutions to the circuit. Okay, so that's kind of what you've been working on up to now, so that will be the same. Any questions about what the content will be? All right, so Amy described how to solve them by finding the transfer function and then looking at that to look at the roots to determine if it's overdamped, underdamped, or critically damped. So this is a table that is supplement to that, where if you solve the characteristic equation and find your roots, it looks at just the 2 alpha and omega naught, which is what's in there for the square root portion. And if you're in series or parallel, it's always going to be of the form of this either R over 2L or 1 over 2RC. The R in that can sometimes be kind of tricky to find. And so if you do it as the analysis that she gave, that's fine. Or if you want to find that Thevenin equivalent R, you can do it that way instead. So whichever way you like to do it to determine whether it's overdamped, underdamped, or critically damped. Once you determine series or parallel configuration and then which one it is, you can use the equations. And so with those are the description of the equations. And so I think she showed you these solutions. But it wasn't in the table form. So I just wanted to show you guys this if you wanted to use the table form. All right, so one of the things that I found students sometimes struggle with is even identifying, is this circuit in series or in parallel for the configurations? So that's what we're gonna go through first. So determining whether this is series or parallel or neither. So for this one, is this in series, parallel, or neither? Any other thoughts? Somebody said depends. Okay, so not so confident. I'm hearing. Okay, yes.
Kind of both, depending on what items we're looking at.
Okay, so for these, you're always going to look at the end time. So with that, you're going to put the switch in the end position. So maybe that will help you. So in that case, where will the switch be? Okay, there you go. Okay, so it's the end time is when you're looking at it. So when you're looking at t is greater than or equal to 0, that would be the end position of the switch. So I did hear people say series. So yes, in this case it would be series. Okay. So not parallel. So series. Okay, what about this one? So this would be closed. So what makes this one tricky is that in order to be in parallel, they need to have the same voltage across both their branches. In series, the same current would need to flow through them. Correct, neither in this case. Okay, so you can see like the same current won't flow through those in the final position. And then the voltage across either, it would need to be the resistor and capacitor or the resistor and inductor, and then the capacitor on the other side. So that would be the form for parallel. So it's a neither in this case. Okay, this one. Blank looks. Okay, looking at this, I will give you a hint. There's two different circuits here. So for this one, that would be series, correct? So they have the same current going through them. So same current. So that would be series. This one, should I do a different color? Is not an RLC. This would just be an LC circuit. Or not an LC, RL circuit. So just a resistor and inductor. Okay, this one. So switch would be open. So these would be parallel. Or sorry, no. Yeah, I have a little jet lag. Series. So with that not connected, they're just gonna go through the same current. So only one current is flowing there. So that would be series. Neither. Good job. So neither. So this has an RL over here. And this one has an RC. So that would be neither. So this was meant to actually go the other way. So I will open this up for you. So that was meant to be open like this. It's what? So this one's a little trickier because what happens with the inductor after it's sat there for a while? It would be a wire, so it would actually bypass the 5 ohms and you would ignore that one. And so it would be in series, correct? So this one would be parallel. So unlike the other one where it had, let me go back to that one. This one where you just have the single branch. This one has the resistor in between them, so you actually get 3 different branches. So because of that resistance, it does cause them to be in parallel. Does that make sense? Still clear as mud? Okay. All right. So I think that on the book ones, you can get an idea of some different circuits on there. So if you want to use that to say, you know, is it series or parallel, that will give you more practice also getting through these to identify if they're series or parallel. I think you have to solve the circuit, but you can guess what it is and then look at the solution to at least see is it series or parallel. Okay.
Wait, so like, I guess why exactly, like, for the last one isn't parallel? It's like, won't the like, inductor bypass the like resistor, the VR, after a long time?
So yeah, that was kind of confusing the way I set it up here. So from this one, when it bypasses it though, all the current is going to go through just the one pathway. The difference here is that with those, even if it is a wire with the 8 ohm or through the L, there's still going to be different current going through the 8 ohm. Let's see, how do I start this? Thinking if you want to look at it more like lumping up where the element is might be better than looking at the bypass. So looking at where the element is, hopefully this is easy to see, like, yeah, that's in series. Looking at where the element is here and here, again, like that's going to be neither. Here and here, that's pretty easy to see, like those are easily seen in series. And here and here. So this would be an example. If I had this closed, what would these be? They would be in parallel in this case, if that was closed. But with them open in the end, these would be in series. Those are just RNL. So this one is a little bit more confusing, like, is this neither or is this, so hopefully you can see, like, it wouldn't be parallel, right? Because those are not in parallel form. So it would either be series or neither, and maybe that is a little confusing, whether they're series or neither. So I'll put so with knowing, like, whichever one you're like, I don't know which one it is, then you would go with the neither. You would change them to the S domain and then create a transfer function from the S domain to then determine what they were. This one, hopefully you can see, like, the elements themselves are in parallel. So whether that is a resistor or some other element in between them, it still creates them in parallel because you have 3 branches.
Oh, that's good.
So it's because there's 3 branches there that they're in parallel.
Oh, okay, I see. Oh, yeah, like, I guess if you move VC down to the red line, then VC would be all in line, I guess.
Yeah.
Sounds good. Thank you.
Does that make more sense?
Yeah.
Okay. Okay. So looking at this, we want to find the expression for VC of t. And so with that, need to know, like, is this series or parallel if you want to go that route first. So what would this circuit be? It'd be series, correct? Okay, so then how would you solve this? Okay, so you could set up the transfer function. I actually find it a little easier to, so using the table, I just would need to know what my initial value is, and then finding alpha and omega naught from that. So I'm going to show you a slightly different way to solve it because I think it's a little easier. So with that, I use the final circuit. So this means this is going to be open. And then I take out both elements and find the Thevenin just the two elements C. So in that case, this is not connected. This will be a short, and my RTH would just be 12 ohms. And then from here, I identified that it was so with its series, it's just R over 2L. And so this would be an alpha of 12 over 2, and then L was 0.1 Henry. So this would be 60 Nepers per second. And then this would be 1 over square root of LC. And this was 0.1, and C was 1 over 360. So that ends up being 60 radians per second. And so these are equal. So this would be critically damped. Okay, series critically damped. So then I can use just these equations here. So I need to know VC of 0 and VC at infinity, and then IC of 0. So going to time equals 0, right before the switch, which is closed. This will be a wire, this will be an open. And what would VC be here? What's here? Somebody say it louder.
60 ohms.
How'd you get 60? Oh, you added the 2. So there's current here and here. So it won't be 60. I'll do them this way. Across the 6 ohms, what's the current? 0, correct. So I can ignore this. So I could set up my equation with this as the node and do VC minus 36 over 6 plus VC minus 24 over 6 equals 0. and that solves to 30. Or I can label the I and do a loop and solve for I, and then do 36 minus I times 6, or plus 24 plus I times 6. Either way. I like to just write the one equation. So VC is 30. Then in 0 plus, oh, I guess I still have to find IC though. So this IC will be 30 minus 24 over 6, which is 12, 2? No, 1. $14. Yeah, 1 amp. 12. Okay. Does not look right. Okay. So 6 divided by 6, 1 amp. Okay, so with this one, when it's open, this is still going to be 1 amp, and this will be 30 volts. So my IC of 0 will still be, or my IC of 0 will be the 1 amp. Or minus 1 amp, sorry. So it's going to go this direction. And then our final one, there's going to be no current, right? Because everything's open. So what is VC here? Correct. So that will be 24 volts. So VC 0 and VC infinity, this is going to be 30 was 0, and then the infinity was 24, so that will be 6. And then B2, 1 over C, which was 1 over 360. So we have 360 times IC of 0, plus the alpha, which was 60, and then 30 minus 24 is 6. So this becomes 360 times minus 1. So minus 360 plus 360 equals 0. So this becomes VC of t equals B1, which is 6, plus B2, which is 0t, e to the minus 60t, and then plus VC of infinity, which is 24. So this can be written as 24 plus 6e to the minus 60t in volts. So this would be my expression for this one. So in this case, it would be this first answer. All right, questions on these steps? I know these are a little different than what Amy did, but I find this easier than doing the transfer function.
How do you find VC again? Is it just like a current divider?
So here,
Yeah.
so this is a node voltage, so I took the currents. Let me use these. So I took the currents out of each of these nodes. So this current can be expressed as this voltage here, which I called VC, minus the 36 over 6. So that's that current. Let me color this different. I'll do it with green. And then this current is VC minus the negative side of it, which is 24. So it's just taking the voltage using Ohm's law of the voltage across the resistor divided by the resistance.
That's good.
Does that make sense?
Yeah, and I guess we equate it to 0 because like there's no current going through the open branches.
Correct, yeah. So this would be plus 0 equals 0.
Sounds good.
Yeah. So this description and this equation is called node voltage. So if you look in the book on the node voltage chapter section, it will describe it. So all it is combining the summation of currents with the voltage loop. All right, questions? Okay, guys do this one. Okay, so we already looked at this. This is two circuits once it's closed. On the left, it's going to be series, and on the right, it will be an RL. So for this, you're just looking to describe the VC of t. We'll just find VC of t. So don't worry about IL of t. For when t is greater than or equal to 0. Yeah, so there's not going to be homework this week because of Thanksgiving, so instead I'll just put out the practice problems for Unit 4, and then you guys can work on those on your own and use that to help prepare for the exam too.
You said no what?
No homework
Oh,
this week
visitor.
or quiz.
Okay.
Yeah. And there was no quiz last week, as you noticed. I did not have any access to internet, so we gotta skip a week.
Was that homework 22 not due this week?
It was due,
It's due today.
oh, it was due today, so
Oh, it
yes.
was set to be
Sure,
due
she
for
changed
Tuesday.
it, she changed the due date last week, because we had to redo on Thursday, and she changed it to be due on Tuesday this week.
Okay,
Only like the 22, not
yes,
20.
so there's no homework for 24, but yes, if she changed that, then it will be due today. So homework lecture 22 is due today, and then you won't have any homework this Thursday or Friday, or quiz.
Same for next week. So there's no
So there's no more homework, correct?
Oh,
No more homework after 22.
Perfect.
Will we also, for the exam, need to know how to do the transfer function as well as this method?
Whichever method you
It
like
just
to
either
use.
or?
Yeah.
Okay.
Yep. So if you wanna go through and find the transfer function method and then solve it from the transfer function, that's fine too. It should be the same equation.
Go.
Yeah. So either or, whatever method you prefer to use is fine.
I just have one question. Will like transistors be on the exam?
So now I'm trying to remember, what did I ask you in exam 3? Were they on exam 3?
No.
Okay.
And they weren't all that.
I'm gonna look at that. So, I had transistors right before the exam, right?
Mhm.
Yeah.
Yes, I take that back, transistors will be on the exam. So, yes, I will add those in for the practice problems. So what did I ask you for transistors now? I'm trying to remember the homework I asked. Yes, we did solve transistors, we only did BJTs in here though, right? Yeah. Okay, so yes, you will need to know how to solve transistors. We looked at, so identifying if it was in cutoff, active, or saturation mode, and comparing them to know what stage they were in, and then finding the current through them. So yes, there will be some a transistor question. We'll add that. Cause I forgot we had that before the exam, which is why I forgot about it. So I will add in questions that would be kind of expected on the practice problems, because I did not have one for today. BJT transistors. So solving a BJT circuit and identifying the correct state it's in, and then finding the current going through it. Could be asked.
So for this, you remember the transfer function method? Would your P after whatever after the switch is closed, or after T is zero, right?
Yeah, so you put it in its final state and then solve it.
Everything will be fine today.
Put it in the final state and then find the transfer function.
And assume, final state is okay, cool, awesome.
And then that will help, you can find the characteristic equation on the bottom, to determine if it's underdamped, overdamped, or critically damped, and then you know the formula of the final solution. And then you come up with a table of ones with find those values. Anybody solve this yet to see which characteristic it is? Anybody get that part? Okay. Okay, so we already identified previously that this is going to be series. So we're going to use the same, and this was closed. So this is going to be closed. And then you have both elements in series together. And then, so this would be your final circuit. So RTH in this case will be 12. And so alpha will be again 12 over S2 times 1 milli, which ends up being 6 times 10 to the third meters per second. And omega naught is going to be 1 over the square root of 6 micro, which is 10 to the minus 6, times 1 milli, which is 10 to the minus 3. So that ends up being 12,000 and 910 radians per second. So if you're going to use the table, the first step is identifying parallel or series. And then from there, find alpha and omega naught, and then compare alpha to omega naught, and this will then determine if it's critically damped, underdamped, or overdamped. So identifying which characteristic you have. So what characteristic? And then from there, you're going to solve the circuit, solve for variables. At t equals 0 minus for your variable, at t equals 0 plus, and then the last one is solve for t at infinity for variable, and then plug into the equations. So those are your steps you're going to take. So we identified it, in this case it was series. I'll put series or parallel. So series or parallel. And then we found omega or alpha and omega naught. And then in this case, what do we have? Alpha is less than omega naught, right? So what do we have? So we have underdamped when it's less than. So underdamped, and then in this one we also have omega D. So we also need to find that one. So we have 12, 9, 10 squared minus 6 times 10 to the third squared. And that ends up being 11,431 radians per second. And then I need VC 0, VC infinity, and then IC of 0. So T equals 0 minus is switch is open. And we have capacitor and inductor. What was over here? And then this is a inductor. So what will IL be here? IL is just a wire, right? So it will be? Thank you, 0. So 0. VC, what's going through here? Current-wise, 0, 2. So VC will be what is, so between here and here is 4 volts. So then we need to know what's between here and here across the 5 ohms. So what current is going through here? 2 amps. So what's the voltage? Between here and here will be, so this will be 10 volts, 2 times 5. So we have plus 4 and then a minus 10. So if I'm measuring this, I measure plus 4 on one side and then I measure 10 volts on the other side of it. So that's going to be 4 minus 10 for a minus 6 volts. So that's my VC 0. And so these have to stay the same for T equals 0 plus. So we're going to have VC of 0 is going to be minus 6 volts. IC of 0 will be 0. And IL of 0 is 0, 2. But those are the values we need as the IC 0 and the VC 0. So final, this will be closed. And this is again open, and then that's a wire. So VC is here. So what's VC here? Current here? Zero again, correct. So with that 0, VC will be right, this is closed. So this ends up being all the same wire, right? So there can't be any voltage drop across there because it's all the same wire. So when I measure it from the plus side, I measure plus 4 and I compare it to the negative side of 4. So that's going to be 4 volts. Do you guys see that? Okay. So this will be 4 volts. So I can then plug this in. Write it here. So VC of T So e to the minus alpha, which was 6 times 10 to the third. And then D1 was VC of 0, which is minus 6, and then minus 4 for a value of minus 10. So we get minus 10 cosine of 11,431 t. And then D2, this was 0. And so this value goes 6 times 10 to the third for alpha, and then a minus 10 over 11,431. So this gives us a value of minus 5.25. So D2 is a minus 5.25, and then sine 11,431t, and then a plus VC infinity, which was a minus 4. Wait a minute. Was a plus 4, sorry. Plus 4. Yeah, plus 4. So this would be our VC of t. All right, questions? Okay, another one? Okay. All right, let's do this one. So VC1 of t and VC2 of t.
Just for the purposes of like alpha and omega knowledge. Because it's R over 2L, right? So you just beta over 2W. It's a lot easier to do it that way.
Yeah, let me get more complicated.
How would you do it with the transform?
So you would,
What would your V out or like what's more
so your P out would be VC1 or VC2. But VC2, you can see when it's open, it's actually this RC circuit
Right.
over there, so then you
On the
would-
right side.
on the right side. And then for the left, you would use, I would do no voltage, and then find the current in there, and then I would take that times the impedance of whatever this.
Okay.
Yeah.
I see. Alright,
So-
not really.
Not for you.
Alright.
Not for you.
So I'm sure if we get asked the transfer function test, it won't be like this tricky, or will it? Should we?
I would say it would be easier to use the table.
Right, like if they explicitly ask to do transfer function, would it be, no?
I wouldn't ask you to use transfer function. The other way would be that it, you can transform it into two parts, so
whatever you define as output, your alpha variable. Yeah, so you could do IO.
If we're finding an item, to use to compare to the input.
All right, so, sorry, we're kind of running out of time. So with this one, hopefully you identified that when it's open in the final state, you're gonna have two circuits. One will be the series, and then one will be RC. So for the series side, when you're finding the Thevenin for it, it's just gonna have 8 ohms. And then you'll do 8 over 2L, so you get 4,000, and then omega naught, and you'll find the alpha is greater than omega naught, so overdamped. In the initial circuit, you'll have this circuit, so you'll have 0 current going through the 3 volts, and to find VC1 then is just gonna have the voltage Vx on the top, which is going to be 2 amps times 8 ohms. You guys see that? So going through here is going to be the 2 amps. And so 2 times 8 is going to be 16 volts. So you'll have 16 minus the minus 3, so you'll have 19 volts there for VC1. And then IL, or where was IL? Oh yeah, IL is the wire there. Okay, so IL1 you're gonna find as no current from the 3 volt side, but then you're gonna have the current going through the 5 and the 10. So 5 divided by 10, so you'll get a minus 1/2 amp, which will go in this direction. So you'll have a plus 1/2 amp going in that direction. So those will stay the same for the 0 plus, and then in the final state, you're gonna have the 16 volts again on that side, and then the minus 3 on the other. So you're gonna have the same voltage as 19. And then on IL0 or IL, you'll have 0 because it will be disconnected from the other side of the circuit. So overdamped, you need IC0 and then VC and VC infinity. And so VC0 was the 1/2 amp, and then the VC1 was 19 and the VC infinity was 19. So those end up canceling each other out. So on these, you end up with 0 on these sides. So A1 and A2 end up just being the 1 over C value times the IC0, which was 1/2. And so you get a 5 times 10 to the minus 4th and a minus 5 times 10 to the minus 4th for A1 and A2. And so this ends up being your VC1. And then you get VC infinity in there, so you get plus 19. And then for VC2, you just have to find the RTHC because it's an RC circuit, and then your final and your initial. So your final for the capacitor over here was, go to this one. So in this case, your VC2 initially was 0 because you have a short across it. And then in infinity, you're going to have 5 volts because you have 0 current in that one. So you have 5 minus 5 ET minus T over tau. All right, questions on that one? Okay. Don't have time to go over the last one, so I'm just going to talk through it pretty quickly. This is the same circuit, except for it's asking for it to be closed at t equals 0. So when you close this one, you end up having these in parallel instead. So you have, oh, actually it's not the same circuit, but you have the inductor and the capacitor has the same voltage across them. So it will be parallel form. So with this one, the difference is that you use 1/2 RTHC. And then the RTH in this, you have to consider both the 5 and the 8. So this is the final circuit. So you have a split. So you have 10, and then you have the branch with the 5 and the 8 added together for 13. So you're going to have a 13 in parallel with the 10. And then the current source becomes an open, and then the voltage sources become wires. So this is your equivalent circuit for that. So then you have 13 in parallel with 10, which gives you 5.65. So you use that resistor value. And then in this case, you end up with alpha is 0.9 and omega naught is 100. So you get underdamped conditions for this one. And for t equals 0 minus, when you do the node voltage, you have the current going in as 2, so it's a minus 2 when you take that one. And when you take this one, it's going to be Vx over 8. And pink. This one, you're going to have Vx minus a minus 3 over 5 equals 0. So that would be your equation, and solving it for Vx, you get 56 over 13. Your current is going to be the pink branch, so you have Vx plus 3 over 5. So that's the same as the pink branch, and that gives you 1.46 amps. And so this one, when you replace them for t equals 0 plus, you use the 56 over 13 and the 1.46. And so those end up giving you a VL of 5 and an IL0 of 1.46, so that will stay the same. And then for your final circuit, you have this one, so you end up with the 16 minus a minus 3 over 13, and then a plus IL plus 0 minus 5 over 10. So you have to add up those currents to get IL. And then you use an omega D, you calculate, and then plug in your values for the IL and the VLs. And you end up with this end equation. All right. That was a really quick talk through questions. All right. Okay, I'll see you guys next Tuesday. Have a great Thanksgiving.
So I think